Hi, welcome to the third episode of our series on quantum physics. In our last video, we checked the four fundamental forces that mediate all interactions between particles. Today, we will see what particles those are, which is why we are learning about the standard model of particle physics. In an atom, you know there is the electrons and the nucleus. The latter is formed by protons and neutrons. The thing is that, while electrons cannot be divided into something smaller, neutrons and protons can, which is why they are not elementary particles. The standard model of particles physics describes the elementary particles. There are 17 in total, so let's go bit by bit. There are mainly two types of particles, fermions and bosons. To simplify, fermions are what matter is made of, and bosons what makes matter interact with other things. Electrons, protons, and neutrons are fermions, and photons are bosons, for example. Our first fermion today is the electron, which, as you know, is characterized for having a negative electrical charge. Well, and basically making all of chemistry work. Protons and neutrons are composite particles made of quarks, which are over here. Normally, we see up and down quarks. Two up and down quarks make for a proton, and two down quarks and one up make for a neutron. The cool thing about quarks is that they cannot exist isolated. They attract each other so strongly, thanks to the strong nuclear force, that if you try to separate them, the energy between them is so big that new quarks appear just to keep the others paired. I guess they love company that much. There are other types of quarks that make for more uncommon particles. These are the charm, strange, top and bottom quarks. Quarks can also exist in groups of 4 or 5, instead of 3, but these particles, tetraquarks and pentaquarks, are very exotic and have not been detected outside human-made experiments. Moving down again, we find the leptons, which do not undergo strong interactions. There are three types, or flavors, of leptons: electronic, muonic, and tauonic. For each of these, there are two particles, one with and one without charge. The three charged leptons are the electron, the muon, and the tauon. These are very similar. They all have a negative electric charge of -1, but the muon and tauon are much heavier, and also unstable, than the electron, about 3,000 times heavier. The three non-charged leptons, on the other hand, are neutrinos. We find the electronic, muonic, and tauonic neutrinos. Original names, I know. These are very elusive particles since they barely interact with matter. In fact, if you wanted to stop half the neutrinos that pass through a lead leaf, you would need a light-year-long brick of lead. Because of this, neutrinos are really hard to measure, which is why we build these huge detectors. Okay, so far we've got 6 quarks and 6 leptons, which make up for the 12 fermions there are. So let's go with the bosons. In the last video, we saw the fundamental forces. Bosons, as I said, make particles interact with each other. So for each fundamental force, we find a boson that mediates that interaction. Electromagnetism is mediated by photons, which are right here, and strong nuclear force, which keeps the quarks in a proton and the protons in an atom together, is mediated by gluons. Weak nuclear force, on the other hand, is somewhat special and gets 3 bosons, W+, W-, and Z. The two W bosons have an electric charge of either positive or -1, and the Z boson is neutral. And finally, the coolest of the bosons, the Higgs boson, which was theorized in the 1960s and discovered in 2012. The Higgs boson explains the Higgs mechanism, which generates the mass of an elementary particle. So thanks to the Higgs boson, particles have mass. But how do objects with mass interact with each other then? That, my friend, is gravity, and it is the main problem of quantum mechanics. We have not been able to explain gravitational interaction within this standard model, but we have with general relativity. The problem is that the latter cannot describe quantum phenomena. Because of this, there is a last hypothetical particle that would mediate gravity, the graviton, but we have no evidence of its existence so far. In the next video, we will learn about the Pauli exclusion principle, which differentiates how fermions and bosons interact with particles of their own kind. So follow us and keep tuned.